Hi, today we are going to look at some iterative methods for finding optimal policy in Markov decision processes. A quick recap first. Recall that we defined the value function of a policy. The value of a policy at state S was defined as the sum of expected discounted rewards starting from state S if you follow policy pi. And we saw that the value of a policy is in fact given by recursive equations called Bellman equations, where the value of policy pi can be expressed as the sum of immediate expected rewards for that policy plus the discount times the expected value in the next state. And if gamma is strictly less than 1, then this matrix here is invertible, and then value of a policy can be readily computed as the inverse of this matrix times the reward vector. So now we know how to compute the value of a policy. And let's go back to the question of finding the optimal policy. Firstly, we realize that we haven't defined the optimal policy yet. When starting in state S, we would like to maximize the value of the policy starting from state S. So optimal policy when starting in state S can be found like this. But in general, it is possible that the value function is maximized for different states by different policies. So which one of these should be called the optimal policy? A remarkable result in MDP that we'll now look at is that in fact there exists a single policy that is as good as any other policy for all starting states. More formally, let's define a partial ordering over all policies of the MDP. In this partial ordering, we say that a policy pi is better than another policy pi prime if the value of policy pi or for a starting state S is better than the value of policy pi prime for the same starting state S for all S. And you can imagine that in this partial ordering, two different policies may not be always comparable because each of the policies achieves a better value for one starting state than the other. A useful fact known about MDPs is that in fact there always exists a policy that is at least as good as any other policy in this partial order. We'll call such a policy an optimal policy. This policy achieves at least as good value function for every state as any other policy, and that the value function of this policy will be called the optimal value function and denoted by V star. Now, how would you find such an optimal policy? There are exponentially many policies in an MDP. All possible mappings from state to action forms a policy. So one can not imagine finding an optimal policy just by evaluating by brute force every policy and then comparing them. We need a better way. One of the most fundamental discoveries in the theory of MDP, which forms the basis for optimal policy search, is Bellman optimality equation. These are recursive equations relating the optimal value function to the sum of the best possible expected immediate reward and a discount times the expected value of the next state. This can be expressed in matrix notation as before, where we will use value vectors, immediate reward vectors, transition probability matrix, and optimal value vector again. So then optimal value functions can in fact be computed as a fixed point of this equation. An optimal policy can then be found as the actions that achieve this maximization here. Unfortunately, there is no closed form solution for Bellman equations in general. However, there are efficient iterative solution methods, and today we will look at two of these methods called policy iteration and value iteration.